Hey gang, welcome back from the break. Hope everybody had a good Christmas and a good New Year's and is ready to get started. Uh, Today, I was trying to find an image for The Expanse, and The Expanse is a great series, but it doesn't have like an iconic spaceship. You may say, oh, the Rocinante or something like that, but yeah, it's kind of generic looking. And so I was thinking, okay, I need something from The Expanse. And I went, oh, I know. I'll have Amos watch my back during today's lecture. So um, this is a lecture protected by Amos Burton. So if you guys watch The Expanse and know Amos, you'll know to shape up for class today. Okay, so let's see. What do we need to do today? Well, the first thing is that I want you to do is, if you haven't already done so, please sign up for the meetings tomorrow. Let's see. There are a number of you who, let's see if I can find it. There are a number of you who haven't yet signed up. Here's the sign-up sheet. There's I don't know what, like 16 of you who've signed up. Some of you signed up almost immediately. Let's see, that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. A couple of you got in this morning. But every slot should be filled. So please go ahead and sign up now. If you don't know how to get to the sheet, just go to Moodle and look under assignments, and there is the assignment 1 sign up sheet that's there. So everybody needs to sign up for the meetings. So your programming assignment is due tomorrow morning, right? But also you have to meet with me. So be sure to get your programming assignments in, and also be sure to sign up here. So that was the first big announcement. Okay, so we also need to get ready for assignment 2. And assignment 2 is going to be a modest extension to assignment 1. Essentially, what we're going to do in assignment 2 is there's going to be multiple objects in the assignment that you'll have to build in your program, and the scaling and rotation will need to take place in place, and we'll define what that is here in just a moment. We're going to cover that in today's lecture. But those are really the only 2 things. You'll use the whole framework that I gave you for the first assignment. Why multiple objects? Well, I defined the pyramid for you, right? You now need some practice building objects on your own. Cubes, rectangles, well, not rectangles, 3D rectangles. So cubes or boxes. Simple objects that you can render. So objects without too many polygons in them. So you need some practice doing that. And also remember, when you build your polygons, it's very important that you label the points in the polygons clockwise as viewed from the outside. Go back and look at how I did the pyramid, but that's important. So one thing you'll do is you'll build a couple of objects, and 2, you will implement in-place rotations and scaling, translation. So you'll implement those, and those will need to work on an object by object basis. So that's another change. We only had 1 object to begin with, but now there's going to be multiple objects. So if you rotate like your pyramid, that shouldn't affect your cube or whatever, right? So it's a pretty modest extension to the first assignment, but it'll get us ready for bigger and better things. Okay, so are there any questions before I start going over in-place rotation? Any general questions? You can either type them or ask them. Going once, going twice. Hopefully everybody had a good break. I know I did. Let's see. Okay. So one thing you'll notice is I was a little busy beaver over the break. Let's see. I keep replacing the lecture notes on Moodle. Here's what we're going to cover today, but if you'll notice, the lecture notes are beginning to look more like a little mini book. So I've gone and I've added a table of contents. Again, we're at section 7, page 19. Like I said, my notes for this class were just handwritten that I had pulled from multiple books over the years, and I had plopped out just the best material. But because that material was pulled from different books, you know, the examples weren't consistent in it, and there were other little issues here and there. So I've gone back and tried to rewrite everything so that everything is consistent, and I think that it makes it easier to learn. So hopefully the programming assignments will be. I was talking about how assignment 3 and assignment 4 can be really bears. Well, hopefully with better explanation, assignment 3 and 4 will not be as difficult this time around. Okay, but before we can even think about assignments 3 and 4, we got to get through assignment 2. So we remember that our rotations in our first assignment were not in place. Okay, well, what do I mean by we're not in place? Well, I mean that if you ran the assignments, well, that the objects, the pyramid, didn't rotate in place. Hold on a second. I'm going to actually try to bring up that assignment. I wasn't planning to do so, but let me do that. So you'll remember that this is what our assignment looks like currently, the one that you're building. But if I were to rotate, say, around the vertical z-axis here, well, that's the vertical stuff. That's the axis, the z-axis. I'm sorry, I meant the y-axis. If I want to rotate around the y-axis, the pyramid rotates, but it's not rotating around itself. It's rotating around that imaginary vertical line that is the y-axis, right? And so this is the way everything's supposed to work in assignment 1, but what we want for assignment 2 is I want this guy to I'll make him a little bigger. We'll zoom in a little closer. I want this guy to rotate in place, okay? So I want him to rotate about his own center point. Now I've moved him closer, so when I rotate around Y now, the circle is it's not quite as big. Now, if we wanted to, you could futz around with this until you actually got the pyramid centered so the visual center of that pyramid was at the center of our viewing space. And if you did that, then the pyramid would appear to rotate, naturally in place without moving. But what we want to do is we want to have the pyramid rotate about itself no matter where it is on the screen. So it doesn't matter if it's here or if it's over here in the corner. No matter where it is, when I rotate it, I want it to rotate in place. I don't want it to move. So that's what we're trying to accomplish. So instead of it moving right around that y-axis, we want it to be in whatever position it is in, but just rotate right where it's at, like in place. Okay, so that's what we're attempting to do here. So in place rotation. Remember, scaling is the same way. When we scaled something, if that thing isn't centered, then you're going to get the same kind of effect. So I guess one more time, going back to our example. Here we have the pyramid, and if I were to scale the thing to make it larger, or smaller or larger, you're noticing that it's getting bigger, but it's also moving.
We can't
we
see
don't want it to move.
We can't see the thing. It's just showing your face right now.
Thank you. Appreciate that. Now you can. But if we make it smaller, it's moving, right? Well, I don't want it to move. I want to make it smaller or larger where the visual center of it still is right there. Right, so that's what I want, and that's not what we get if it's off centered. But now notice, if we do have it centered, like it is here, right, in X and Y, scaling it looks natural. It's not really. It's not really. I guess it's moving a little bit, but it's not moving a whole lot. The center is still moving a little bit. Okay, so how are we going to accomplish this? Well, we're going to accomplish this by a little trick. We've already shown that our rotations and our scaling are in place if the object is centered on the origin. So if the visual center of your object is 0, 0, 0, then the object will scale or rotate without moving. So what we're going to do is we're going to do a little dance. We'll take our object. In this case, we're going to start with a two-dimensional triangle. We're going to take our object, and then we are going to move it to the origin. What we're really going to do is we're going to take the reference point. So in this case, I've got an object. It's a little pyramid here. And instead of setting the reference point exactly in the middle of that triangle, I set the reference point here. Well, what's the reference point? The reference point is the point about which the scaling or rotation will take place. Okay? So if you want the rotation or the scaling to be completely, perfectly, visually in place, as in the object not moving, then you will need to have your reference point be at the visual center of the object. You might be saying, Mike, what's visual center? We'll define that in a moment. But for right now, we'll just say, okay, I've got a reference point that I'm giving you, and I've got an object, and I want to scale or rotate that object around that reference point. So the first thing that has to do is, once you've got an object, and our object here is a triangle 2, 2, 3, 3, 4, 2. So I did it clockwise, right, as viewed from the outside. Of course, this is two-dimensional, so there's not a Z. You can think of it as 3D, where we're just playing in the Z = 0 plane if you want to. But anyway, so we've got a two-dimensional object here. It's triangle, it's polygon. I've defined a reference point at the bottom of it, centered bottom, and I defined the thing clockwise. Is this the only way I could have done it? Well, instead of starting 2, 2, 3, 3, 4, 2, I could have started here at the top with 3, 3, 4, 2, 2, 2. So it doesn't matter where in the sequence I start, but I do need to define the thing clockwise for reasons that will become important later on. Okay? But we always define, in this class, we always define our polygons clockwise when viewed from the outside. Okay, so the first thing I do is I take this object and I move it to the origin. So the reference point will move to the origin. After I've done that, I then perform my rotation. We're going to do a 90 degrees counterclockwise rotation. So my object here is blue. I don't know if you can see it, but in green, I have green dashes. I have the rotated object. So basically, we take this object here and we rotate it 90 degrees. So this point, that's the apex, moves over to here. And this point that was here moves over to here. And the point that was here moves over to here. So this thing goes sideways. It goes from right side up to sideways, pointing to the left. So we did our rotation. And you notice that it's a rotation that is around the point here at the base of this pyramid. So the object didn't move, it rotated around that point, which is what we wanted to do. The next thing we do, the last step we do, is we take that reference point and we move it back to where it was originally. So what this shows is, in light gray, you see the original triangle, and in green, you see the rotated triangle. So we did it in 3 steps. Step 1, move the reference point to the origin. Step 2, perform the rotation using the standard rotation equations. Step 3, translate it back. Okay, so that's what we want to do. So how do we do it? Well, it's pretty simple. Actually, it's very simple. The first thing you have to do is you have to translate. Okay, well, we're working in 2D, so our translation equations here are, and we've got a reference point. The reference point is 3, 2, 5, and we want to move 3, 2, 5 to 0, 0, 0. So that means we have to subtract 3 in X, we have to subtract 2 in Y, and we have to subtract, sorry, that's, hold on. So it's 3, it's 3, 2. 3, 2.5 would be if I had put the point right there. So I'm misreading my notes. The reference point is 3, 2, as you can see here. So because it's 3, 2, I want to move 3, 2 to 0, 0. So I have to subtract 3 in X, and I have to subtract 2 in Y. Okay? Now, this is the equation that'll move the reference point, but we would have to actually take each of the 3 points that make up the vertices, and we would have to apply this equation, these 2 equations, to each of them. So 2 minus 3 becomes minus 1, and 2 minus 2 becomes 0. So the point 2, 2, right there, becomes minus 1, 0 right here. And then 3, 3, which is the apex, right, which is here, 3, 3, subtract 3, so that becomes 0, and then subtract 2, that becomes 1. So 3, 2 becomes 1, 0. Sorry. I have dyslexia. 3, 3, which is right here. It's our apex. 3, 3, subtract 3 becomes 0, subtract 2 becomes 1. So 3, 3 becomes 0, 1, as you can see right there. And 4, 2, which is the point right here, subtract 3 from the 4, you get 1, subtract 2 from the 2, you get 0. So this guy over here becomes 1, 0. So if you use this little equation for x and for y and apply that to the points, you get the 3 points, the 3 vertices move to here. Okay. The next thing that we need to do, so that was the first thing. All you're doing is you're taking your reference point, which is 3, 2, and you are subtracting 3 in x and subtracting 2 in y. That's all you're doing. So if it were 3-dimensional and you had a z of, say, plus 5 for the reference point, you would have a tz of minus 5. So anyway, we move the reference point to the origin, and we carry all of our other points along with us. We then apply, in this case, a 90 degrees counterclockwise rotation. I chose 90 degrees because that makes the math work out easy. It's been a couple of weeks, I know, and you probably haven't been thinking about this except for your programming assignment. But go back and look at the equations for rotation, right, about the z-axis, and you see that this is the equation for x, and this is the equation for y. And if you're rotating by 90 degrees, cosine of 90 degrees is 0, cosine of 90 degrees is 1. And so basically these are our formulas. So now if you plug in not the original points, but the translated points, minus 1, 0, 0, 1, and 1, 0, you plug these translated points into these formulas, you get these rotated points. So minus 1, 0 becomes 0, minus 1. So this point in blue moved over to here. And the point 0, 1 is going to move over to here, to minus 1, 0. And the point 1, 0 is going to move over to here, 0, 1. So we flipped this puppy by 90 degrees. And then the last thing you have to do is you have to take those points that you rotated and you have to plug them into the equations that will translate back to the original location. So the points you got out of the rotation, you plug them into these equations. So you take 0, you add 3 to it. You take minus 1, you add 2 to it. So 0 minus 1 becomes 3, 1. Minus 1, 0 becomes 2, 2. 0, 1 becomes 3, 3. And that's how you got your rotated in place polygon. Okay, so let me look real quick here. Okay, so Andrew's saying I may be getting ahead of myself, but the calculations of the reference point should be part of step 1. In this case, I'm giving you the reference point. So there was no calculation, Andrew. I gave you the reference point as, what, 3, 2, right? But we'll talk here in a little while about what if I don't give you a reference point? Is there a way that you can come up with a reasonable reference point? And the answer to that is yes, there is, and we'll talk about that. Okay. Any questions at all about this first example here where I did a in-place rotation? It's very simple. you have some original object, you have some reference point. In this case, I gave you the reference point 32, and what you want to do is you want to do a rotation around this reference point. You have to take that reference point and basically negate each of the x, y, and if you had a z, the z values, let those be your translation factors. That'll take that reference point and move it to 0, 0. You then do your rotation or your scaling, and then after you've done that, you translate it back. So instead of -3, -2, you translate by 3, 2 in this case, and that gets you back where you started. Okay. Now that was for two-dimensional rotation. Scaling works exactly the same way, only instead of rotating, you'll be scaling. So let's say that we had this blue triangle here. And this time I'm actually putting the reference point at its visual center. So what's our little triangle? Our little triangle is 0, 0, 3, 3, and 6, 0. So this is our little triangle. Now, if I were to scale it, I think what I'm going to do here is I'm going to shrink it by 50%. Well, if I were to shrink it and not move it, it would get smaller, but would also move in this direction towards the center, which I don't want it to do. I want it to stay where the reference point stays right there, but I want to shrink it. And why am I shrinking it? Well, we're doing an in-place scale by 0.5. Since that's less than 1, it's going to make it smaller. Since it's 0.5, it's going to shrink it in half along each of the two dimensions. So it's exactly the way it would work before. I'm giving you the visual reference point as over 3 up 1.5. So the center's here. There's no reason that all of these numbers have to be integer. They don't have to be. So you could have a 1.5 and y. And so basically I'll need to subtract 3 from x, and I'll need to subtract 1.5 from y, and that'll get this reference point here in the center here at the origin. But just like before, I take these equations, I plug in the points, the original points, and then I get these translated points. So the original 0, 0, since I'm subtracting 3 in x and 1.5 in y, becomes, as we would imagine, right here, -3, -1.5. And 3, 3 will become 0, 1.5. It'll become the apex right up there. And 6, 0 will become 3 minus 1.5. So these are the translated points. Now you just apply the scaling equations. Scaling equations where you're going to scale in both the x and the y dimension by 0.5. So we do that. That gives us these points here. So I hope you can see it. Here's the original polygon, well, the moved polygon, the translated polygon is now drawn in blue, and what we're going towards is drawn in green, and you can see that it shrank. You've got a little, I don't know if you can see it very clearly, but you've got a little green triangle there. But notice both the bigger blue triangle and the little green triangle are both centered on the origin, okay? And then the last thing you do is you take those scaled points and you pipe them through these equations, and that puts it back, the reference point back where it originally was. And now the original triangle, I have it outlined in light gray, and you can see the new shrunk triangle, and it didn't move visually. It's still located about that center point. Okay. You might say, if you're looking at the equations, Mike, aren't your variables slightly different? What are these A's and what are these B's? All I'm showing you here is there's a little pipeline, right? When you translate your original points, call it X and Y, right? Well, that'll give you an XA, YA. and XA, YA feed into these that give you XB, YB, and XB, YB feeds in to these, which gives you the XC, YC, which is your final point. So those little subscripts A, B, and C are showing you that it's a step-by-step process that you're going through. So these equations don't just exist out in the ether. We're using them as a little pipeline where you translate, then you scale, then you translate to the origin, then in this case you scale, and then you translate back from the origin to the original reference point. Okay. All right. Questions about that? Did that make sense? Do you have any questions about two-dimensional? So far we've done two-dimensional rotation and scaling. It's very, very, very simple. Instead of just doing the rotation or the scaling, you're going to do a three-step process where you get a reference point, or you'll be given a reference point, or you'll compute one. We'll talk about that in a minute. But you take a reference point and you move that. I guess I should go this way. You move that to the origin. Okay. So when we move our reference point to the origin, and you would have to then apply that to each of the vertices of your polygon. Then in step 2, you do either the rotation or the scaling, but now you're doing it about an object that's centered on the origin, so everything will work out right, because scaling and rotation are in place only when you're at the origin. And then the last thing you do is you take that origin point and move it back to the original reference point, taking all your vertices with you, and you end up with either a scaled or a rotated polygon that is in place. You might say, well, but Mike, wait a second, doesn't that mean that people are going to see this thing move around? You know, I thought we wanted to do it in place. You're cheating. You're not doing it in place. You're doing a three-step process. And I'll say, okay, yeah, mathematically, I'm taking the thing, I'm moving it, I'm then doing my rotation or my scale, and then I'm moving it back. So yeah, you're right. I did three things. But nobody says you have to render the polygon after this step, or after step 1, or after step 2. No, what you'll do is you'll only render the polygon after you've done all three steps. So if you're thinking about some sort of an animation, I'll have an object, in this case a single polygon that I've rendered, that I've drawn on the screen, and it's this blue thing here, right? And then if I wanted to do an in-place scale by 0.5, I would do the math to move it and the scale and to move it back, but I don't do any drawing. This was my original one. I drew it, and then after doing all three steps, I draw again. So what a user sees is a user sees the original triangle, and then in the next frame or the next step, the next time we draw, it sees the scaled polygon, and yeah, to them, it looks like its scaling happened in place because I didn't show any of the magic or the sausage making or whatever you want to call it that happened behind the scenes. Does that make sense? So, yeah, mathematically I moved it, to make things work, but that doesn't mean I have to render it when I move it. I don't do that. Okay? So that's why we call it in place. You might say, well, it wasn't in place. You moved it, you did the operation, then you moved it back. What's in place about that? Well, from the user's point of view, it'll be in place because they won't see that we moved it and did the rotation about the origin and then moved it back. We do all of that. We do all of that magic behind the scenes. Does that make sense? Okay, are there any questions about in-place rotation or scaling in two dimensions? Well, there's one question. We still haven't said, where does this reference point come from? And we really ought to do an example in 3 dimensions. because all of your actually, I just added the three-dimensional example last night. I went, oh, it's just like two-dimensional. And then I went, yeah, but they're going to be doing all their work in 3D. And students get real nervous if there's anything that they didn't have in the notes. So let's look at a three-dimensional rotation. Now, it's hard to draw a three-dimensional rotation when all I have is something that's flat. Okay, there is a question. So let me address that before I talk about 3D. So Eric asks, so are in-place rotations theoretically slightly slower, or is addition and subtraction almost negligible? From a human's perspective, computers are so fast that you wouldn't see anything slowing down unless you had many polygons in an object. And often we do have many polygons in an object. Okay? So if you were to implement rotation and scaling the way I'm showing it here, it would be slower. In fact, it would be, you could argue 3 times slower, because you have to do a translation of every point, you then have to do the rotator scale of every point, and then you have to do the translation back. So if, you might argue, well, a rotation's mathematically more complicated. Not if it's a 90-degree counterclockwise rotation. In that case, it's even faster, right? Than the translation. Certainly no slower. But if we take as given that every operation, a translation or a rotation or a scale, takes the same amount of time, and it's not a great assumption, but if we take that assumption, then yes, it would be 3 times slower. So 3 times slower than 1/millionth of a second isn't gonna make a difference for a single polygon. I don't know if it's a millionth of a second. I'm just saying a very tiny quantity. But if you have millions of polygons, so now you're talking about a second, right? Well, 1 second versus 3 seconds is certainly very noticeable. So you'll remember that before the break, I kept saying the thing that's important in computer graphics is speed, faster. Because the faster you can do an operation, the more polygons you can have on the screen at the same time, which means you can make your polygons smaller, which means you can make your polygon meshes more realistic, which means you can get more detailed figures, or for those students who depend on, 144 frames a second or something completely ridiculous like that I'm never going to forget, you can do more frames a second. So you should be worried, Eric, I'm glad you asked the question, you should be worried that, hey, isn't in-place operation slower? And that should be in the back of your mind, because you could be saying, is there some way that we can make it be as fast as just a regular rotation? How can we speed this process up? You should be thinking about that, and that will lead very well into what we're going to do in the next lecture. Okay, so yeah, we're slowing things down, and we would like not to do that. So that's a question for later. Is there some way that we can get the same benefit without slowing things down? Right now we don't know, but what I'm giving you works. Okay, so what are we doing here? We're going to do an in-place 3D rotation about a point. So again, I'm trying to show you this. I'm not an artist, and I'm trying to show you this on a flat screen. So here is our coordinate system. We've got an X going off to the right. And I see that just as I'm about to start going through my graphic, my internet connection goes crap. Remember, these lecture notes are on Moodle, so you should always, as a backup, when we begin lecture, bring up those notes and have that available on your screen. It probably looks a little clearer than looking at the video of me going through it anyway. So while we're waiting for it to reconnect, please go, if you don't already have it, and grab the diagram. So I'm going to assume that you guys either have the notes in front of you or have run over to Moodle real quickly and grab them. And I'm marking time so you can do that right now. And now I'll assume that you've gotten down to page, I guess this is 21. So looking at this diagram here, you can see that X goes off to the right, Y is vertical, and Z goes into the distance. Well, if we were truly looking at this, you wouldn't be able to see Z because Z would be pointed directly away from us. So we kind of shift things a little bit we shift things a little bit so that we can see the Z's. And all of those little dashed gray lines are just to help you see that where I've drawn things on the screen actually makes sense, and to help you see it more in 3 dimensions. So the first thing to notice is that the object or the reference point that I'm working around is the green dot that's sort of towards the upper right hand corner. That's the reference point, okay? So that's the reference point. Let me see if I can rejoin. I don't know if my internet's back, but I'm going to check. It's weird because my internet's saying that I have internet access. I don't know what's going on, but again, sorry about the technical snafu. But if we're looking at this, again, the green point is the reference point, and it's at 532. Okay. Now the point that I want to rotate is the point 554. So it's a little higher than I am, right? So it's up 5, not up 3. It's still the same over in X. It's 5 units over in X, and it's further out in Z. So my reference point is 2 units forward in Z, but the point that I'm going to rotate is 4 over in Z. And if you're looking at the diagram, you see that what I really want to do is I want to do a 90-degree rotation. So you see the little 90 degrees there, and what will happen is 554 will become 334. If I do a 90-degree rotation about the point, the reference point 532. So all of that is what's happening over here in the upper right-hand corner of my diagram. Now, of course, I can't do that operation in place, right? So I've got to still do my same old three-step process. I've got to take that reference point 532 and I've got to move that to the origin. So that if you look at the sort of the lower left corner of the diagram, you see that there's a green dot at the origin, okay? So we see that green dot that's at the origin, you see that the point 554 is actually now, if you translate it, will be at 022. Well, that makes sense because, again, if our reference point was over 5 and x, and our point that we want to rotate is over 5 and x, well then, once we move our reference point to 0, 0, 0, well, the x value for our reference point is going to be 0. You also note that our reference point was at a z of 2, and the point that we want to rotate is at a z of 4. Well, if you move 532 to the origin, well, then that point is now not going to be 4 in z, it's going to be 2 in z. So that's how you get 0 something 2. Well, what about the 2? Well, the middle 2. Well, our reference point was 532, so it was up in y by 3, and the point we want to reference is up by 5 in y, right? So the difference between a y of 5 and a y of 3 is 2. So that's why 554 becomes 0, 2, 2. Then when we do the rotation of 0 to 2, that'll be minus 2, 0, 2. Or sorry, minus 2, 0, minus 2. Okay, sorry. Minus 2, 0, positive 2. The z doesn't change, right? So this point here, the blue one marked 0, 2, 2, moves over to minus 2, 0, 2. So that was the rotation. So what would actually happen in practice is our initial reference system, our reference point 532, would be moved to the origin. Along with that, 554 would be moved to 0, 2, 2. We then do the 90-degree rotation counterclockwise. That gives us minus 2, 0, 2. And then we do the translation of the reference system back to its original position, and that gives us 3, 3, 4 as the point. Does that make sense? By the way, since I can't see anybody, would someone please speak up and say they're hearing me okay?
Yeah, it's good.
Okay. Hopefully everybody was able to find the notes, and once you had those, we're able to follow the oh, it looks like my video's coming back. So hold on one second. Okay. Looks like we lost Amos, but we can live without Amos. Okay. Sorry about that. It's always a pain when we lose it, but at least because we have audio, we can keep going. Okay. So again, this was the original reference system over here. We took this reference system, we moved it over to the origin, so the reference point 532 was at 0, 0, 0. We then did the 90 degrees counterclockwise rotation, giving us minus 2, 0, 2. We then took this system with the rotated point, moved it back here, And that's how we got 334. And the math for it is just like we had before. The only difference is now we've got a z component, right? So you start with some point, px, py, pz. You subtract off the reference point, reference x, reference y, reference z, and that gives us xa, ya, za. So if you do the math there, xa becomes 0, 2, 2, and that's how our original point, after you've done the 532 to here, that's how the input original 554 becomes 0, 2, 2. That's right there. You then do the rotation, and I made it simple since it's a z-axis rotation, and everything lines up. Basically, all that happens is here is, that's a typo. No, it's not a typo. ZA becomes ZB, and it has the value of 2. And then you move it back, and that's how you get the 3, 3, 4. Are there any questions about how that worked? Any questions at all? Okay. All right, so the last question, well, there's 2 questions. The first question is, okay, where does these reference points come from? You're just pulling them out of your, and yeah, I'm just making them up, right? But normally when we've got not just some random point that represents the vertex of some single polygon that exists in a polygon mesh that defines an object, right? Normally we have objects that are composed of multiple polygons. How do we get a reference point? Well, the answer is there is no algorithm for computing the visual center of an object, okay? There's no algorithm for computing the visual center of an object. And the reason for that is, what do you mean by visual center of an object, Mike? Well, normally it's the point in the middle. Well, what does that mean? If you had a long, skinny object, right? Like, let's say you've got some center of something, and then there's like a string, and there's some object here. Okay. Imagine, if you will, a person here, and you know the old thing that you play when you were a kid, where you had a bucket with water on a string or a rope or something, and you would spin it over your head, right? Well, if I were to look at this thing, right, and say, okay, here's the person, and here's the bucket full of water. Where is the center of these things? Well, it's here, but you don't expect a rotation to happen there. You would expect, if you were simulating it, the rotation to happen here. So in this case, even though you've got a person and a bucket with water in it, the visual center is the person. It's not somewhere midway along the rope. Now, that's a exceptional circumstance. Most of the time, if you have an object like, I don't know, a phone or something, right? It's some, object, and it'll have a height and a width and a Z, and phones are pretty flat. But imagine an object, any object. Most of the time, the visual center is somewhere towards the center of the object. So, because of COVID, I happen to have a face mask handy, right? Well, where's the center of the visual center? It's somewhere right around there. It's about in the center of the object, right? So normally what we do, if you're not given a reference point, what you will do is you'll say, well, I know there are exceptions to everything, but in general, the visual center of an object is going to be pretty much the middle point of that object. So what we will do is we'll imagine some object, and we will imagine a bounding box around that object. So the sort of, if we were modeling my fist, the idea is imagine a box, a three-dimensional box, that's the smallest box that my fist would fit into. Take the center of that box and make it the reference point. Okay, so that's what we're going to do here. We're going to create a bounding box around our object, and the center of that bounding box will be the reference point. So how do you build one of these bounding boxes? It's very, very simple. First of all, you look at all of the vertices that make up your object. Look at all of the vertices that make up your object. And go through them and find the smallest x value across all of your vertices. And then find the largest x value across all of your vertices. Now, the x and the y don't have to be in the same vertex. I'm saying look at all of your vertices, find the smallest x, find the largest x. Find the smallest y, find the largest y. Find the smallest z, find the largest z. And once you've got that, you can plug them into a formula that says, okay, to find the center point of this bounding box, you can say, okay, if I take the max minus the min and divide by 2, that'll be halfway in x, and then add in where we started in x. And for y, same sort of thing. Our y center will be, well, this gets us to where the box starts, x minus y, that's the width of the box, divide that by 2. So if we add that to where the box started, well, that'll give us the y center. And then z center is the same way in z, find the minimum z, start with minimum z, that's where it starts, the box starts in z, find the length of that dimension in z, max minus min, divide by 2, add that to where you started, and now you'll have the center point of x, y, and z. So these are the equations. Now, these are the equations that if you think about the problem, you'll probably come up with just off the top of your head, because you're saying, okay, what's the width in this dimension? It's just the max minus the min, divide by 2 will give me the center point. Same thing in y, same thing in z, but that doesn't account for getting to that object. So that's where the x min, y min, z min come from. So if you think about it, these are the formulas you'll probably think of. But if you stop about 5 seconds and think about this algebraically, this simplifies. If I take the x min and I multiply that by 2 over 2, which is 1, right? You can take any quantity, multiply by 1, and you don't change its value. So this would become 2 over 2. That would allow you to put all of this over the denominator too. So you'd have 2x min plus x max minus x min. Well, 2x min minus x min becomes x min. So 2x mins minus 1x min would give me 1x min. So basically, this becomes x min plus x max divided by 2. This formula is a little simpler, and because speed is so important, it saves you a subtraction, right? So instead of doing subtraction, a division, and then an addition, you can do a single addition followed by a division. So I saved you an operation, right, for each of x, y, and z. and we want to be efficient. So you'll probably want to implement this version of the equations. If you implemented this version of the equations, they'll work just fine. They're algebraically equivalent. And then I went here and I said, okay, well, let's say that we've got our pyramid. If you go back and you look at assignment 1, these are the 5 vertices for our pyramid that we defined for assignment 1. What would be the center of that? Well, you find the smallest x. I've got a 0, I've got a 50, so 0 so far, 0 so far, minus 50. Minus 50 is the smallest so far. So minus 50 is the x min. What's the x max? 0, 50, 50 is the biggest, 50 is the biggest, minus min, so 50 is the biggest. So it's between minus 50 and 50 in x. Same thing in y, between minus 50 and 50. And in z, the smallest z, let's see, we've got 100, we've got 50. 50 is the smallest z. And what's the biggest z? 150, 150 is the largest z. So you plug these things in. Minus 50 plus 50 is 0 divided by 2. Gives me a 0. Minus 50 plus 50 also gives me a 0 divided by 2 is 0. And 50 plus 150, that's 200 divided by 2 is 100. So the visual center of this pyramid defined by these vertices is 0, 0, 100. So we are looking directly at the center in x and y, but we have shoved it out 100 in z. Okay, and so well, we didn't need a reference point for the first one. So this would be a good reference point for assignment 2. Does that make sense? Okay. Yes, it makes sense. Good. I'm glad it makes some sense. So what's the assignment? Well, the assignment's basically what I said it would be. It's due on the 14th. That'll give you 10 days to implement it. And really, it's a natural extension of what you've already done. By having you define, so what are the 2 big takeaways? You're going to define multiple objects, and you're going to do in-place scaling and rotation. And we see that in the title, in-place 3-dimensional transformations in a multi-object environment with perspective projection. So the perspective projection hasn't changed. We now have multiple objects instead of a single object, and our transformations are in place where originally they were not in place. So you're just making you're making multiple objects, and you're making the transformations in place. By having you create multiple objects, it will, those of you who are itching to make your code more object-oriented, more modular, this will be a good excuse to do that, so that you can apply operations to individual objects rather than having them be global. So, so part of this assignment is to give you the opportunity, it's not a requirement, but to give you the opportunity to refactor the code base to make it more object-oriented. Doing that will probably help you in the upcoming programs 3 and 4. Again, let me just read through this to make sure I don't miss anything. The purpose of this assignment is to give you experience implementing in-place 3-dimensional transformations in a multi-object environment. It's an extension of what you did in assignment 1 with many of the same concepts, such as the point cloud, the polygon list, the perspective projection. You may want to reorganize or refactor your code to be more object-oriented now that your environment will contain multiple objects. I expect there will be a significant amount of code reuse between assignments 1 and 2. Please remember this is an individual assignment, so Work on it on your own. Do not work on it in groups. So what do you need to do? Correct any problems with assignment 1, as that code forms the basis of this assignment. Populate your virtual world with 3 or 4 simple objects. I suggest using pyramids and cubes. Some students like to get more inventive. I had one student actually write the code to implement a polygonal mesh from the standard format for polygon meshes. That was extremely impressive. He blew me away with that, but he wanted more complicated objects in his program than just simple cubes and pyramids and things like that. So, I was like, okay, things are going to run slow, but okay. So, but that was cool. So minimum requirement is that you populate the world with 3 or 4 simple objects. You must implement the ability to select the individual objects in your world. Probably the easiest way of doing this is via keyboard command or on-screen buttons or some similar mechanism that, every time you press it, you rotate through your objects. So you got 3 objects, the first one is the default, you click a button, now it moves over to object 2, you click a button again, it moves over to object 3, you click a button again, it moves back to object 1. So you need some easy way of selecting what object you want to work on. The selected object should be highlighted in some way. For example, by drawing the edges of the objects using thicker lines or some special color or some other similar mechanism. So we got to have some way of being able to see on the screen which of your objects is the active object, is the selected object. Implement code for in-place 3-dimensional transformations, translation, scaling, either larger or smaller, rotation in X, Y, and Z in both positive and negative directions. These transformations should replace the non-in-place transformations of assignment 1. This is not hard. This is very simple. Where you would have done a z-axis rotation, so when you call the rotate function, within that rotate function, you'll call a translation. It'll take in a reference point as well as, say, the angle you're going to rotate through. And the first thing it'll do is it'll call a translate on to get the reference point to the origin. Modify the point the points that you're working on. Then it will do the operation on those points, and then it will do the translate back. So there'll be those 3 steps will now take place in the operation itself, right? So when you do a rotate, you can have, instead of just let's use scale. Instead of just have scale, it'll be in place scale, and in place scale will call a translate, do the regular scale, and then do a translate back. So you'll do all of that inside the in place scale or rotate function. Okay, so that's basically it. The additional requirements are the standard thing: work independently, develop your own code. You must thoroughly document the program, or Mike will take points off. As in assignment 1, always include comments at the beginning of your main program with your name, student number, the date, the assignment number, and a brief description of what the program does. Comments should also be present throughout the program to explain what each part does. You should also have a comment block at the beginning of each method or class. Programs written in Python must run in Thani, because that's what I'm going to use. Cannot use the NumPy library. Submitting it, you're going to email it to me just like before. The only difference is now it's called assignment 2 rather than assignment 1. It's due no later than 9 a.m. on Thursday the 14th. So it should be CSC470, assignment 2, your name, Leah Organa, if that is your name. And then I'm going to put a sign-up sheet online no later than the day before it's due, so that you'll be able to sign up for appointments. Are there any questions about what's going on here? Any questions at all? Okay. It's very similar to the one that you just are finishing writing or have just finished written right now. So this one's not bad. Like I said, the first two aren't bad at all. It gets more fun as we get to assignment 3 and 4. Okay. Any questions? Okay, well, I have just a couple of minutes left. So far be it from Mike O'Neill to waste even a moment of class time. So I'll give you a little preview about what we're going to do next. Okay. So again, don't forget the sign-up sheet for our current assignment. Okay. What we're going to do on Wednesday is we're going to start talking about another way of representing our equations. You've been given all of the equations now for 2-dimensional and 3-dimensional translation, rotation, and scaling, but I gave them to you as equations. What we're going to be looking at next is representing those equations using matrix notation. Now, if you've played around with matrix math at all, and you should have, if you multiply a point times this matrix here, well, you would see that it would give you these 3 equations. And in fact, these are the equations for translating in X. You'll have a matrix for scaling, and those will give you the scaling equations. And you'll have a matrix for rotation, and those will give you the rotation equations. And we'll be able to do that in 2D and in 3D. Why? Why in the world are we going to now go back and revisit all of these equations and have to think in terms of matrix math? Well, first of all, in your programming assignments, you're not going to have to use the matrix representation if you don't want to, okay? But the reason why we're going to spend some time talking about matrices, there's a bunch of reasons. One of them is that if you ever want to use Direct 3D or OpenGL or anything like that, they all use matrix notation, so you're going to have to understand matrix notation. Okay, so that's a practical reason. A more fundamental reason is that graphical processing hardware, GPUs and TPUs, they are just matrix multipliers. That's what they do. They allow you to compute dot products really, really, really quickly. And so the beauty of matrix operations is they can take place in parallel rather than sequentially. And so, as we will see, using matrices will allow us to be able to take, we're not going to actually use hardware acceleration, but it opens up hardware acceleration, and it allows you to speed up processes by orders of magnitudes, hundreds or thousands or tens of thousands of times. So the reason why, the main reason why matrices are used is because matrix operations can take place in parallel. And whenever you have operations that can take place in parallel, you can build special purpose hardware that do those operations in parallel, and it allows for blindingly fast speed ups. The interesting thing is For those of you who may have taken my AI class either last quarter or last year, you learned that in machine learning, almost everything boils down to matrix operations. Well, guess what? In computer graphics, almost everything boils down to matrix operations, the way it's really used. And that's why graphics hardware, GPUs, were responsible in large part for the explosion in advances in machine learning and artificial intelligence. You developed hardware for computer graphics, and it just so happens that the hardware that we developed for computer graphics could be exactly the same hardware that you needed to do the matrix operations for machine learning. Now, they've split off a little bit, and you have TPUs, tensor processing units, which which keep the matrix operations, but get rid of a little bit of what you need for graphics. So their TPUs are more focused on they can be used for both, but they're a little bit more focused on machine learning. Anyway, we're going to call it quits here. I hope that we were allowed to circle back around to Eric's question earlier about, hey, isn't going to slow things down to be able to do the in-place operations? And I said, well, yeah, but we'll have a way around that. And the answer is well, if you represent things with matrices, we will be able to parallelize those operations and get rid of the slowdown. Okay. All right. Well, I'll stick around if there are any questions, but right now I will call it quits, and we will see you guys on Wednesday. Have a good day.